Here we're going to look at the 4 charges again, and we're going to do it without inspection. So this is our drawing from last time. 4 charges making a square with sides A. 3 of them plus Q, 1 of them minus Q. And the question was, what is the force on charge 4 due to the other 3 charges? So before we said, well, the force on charge 4 is the force of 1 on 4 plus 2 on 4 plus 3 on 4. And we figured out each one and added them up. But we used inspection. We often would say, well, the force of 1 on 4, we know that it points up, just because charges repel and it'll point up. And we know that this one will point to the side because charges repel. And we say, well, we know this one's going to come down. We know it'll be 45 degrees because it's a square. Those are examples of inspection, when you just sort of look at a problem and state that something is true. So sometimes inspection bothers people, and you can do these problems without inspection. So let me show you the key to doing it without inspection is to write Coulomb's law this way. So let's say a force between A and B, any 2 charges, is still Coulomb's constant, Ke. It's still the charge of one times the charge of the other, but it's over the separation between them cubed. You can write it as cubed, but instead of the unit vector, you write the vector A to B. So now the vector is giving you the direction, but it has a magnitude of the separation. So since you have a separation here up top, you have to have another separation in the bottom. So it looks like it's going as 1 over r cubed, but it's still going as 1 over r squared. Okay? But writing it this way lets you do this problem in a way that requires no inspection whatsoever. Okay? So let's just go through and use it, and hopefully you'll see what I mean. So let's start with, as before, F3 form. F3-4 is now just straight Coulomb's law, no inspection. Ke, Q times Q is Q squared over the separation cubed, so that's A cubed, times the vector R. Now in this case we mean the vector R 3 to 4. So what that is a vector that starts at 3 and it goes to 4. Right? That's the vector R 3, 4, and get rid of that A. But what is that vector? It's just a vector that points in the x direction at unit A, the distance A. So that vector is just A times I hat. And then you're done. That's F3 to 4. There's no need for inspection. No need to think about it anymore. We can also do F1-4 is Ke. The Q again is squared. A is cubed. And A is cubed and it's R, 1 to 4. Well, before we thought about repulsion and sticking up, we don't have to do that at all. We just have to say, oh, it's R 1 to 4. There's R. Instead of an A here, I'll put R 1 to 4. What is that? That's a vector pointing up with a magnitude of A as pointing in the y direction. So that's just AJ. So there we have F3-4 and F1-4. And you can see that if you just cancel that A, it's the same answer as last time. Keq over A squared. Okay. That wasn't such a huge leap in simplifying the problem. But let's look at F2-4. That's the one where it really helps. F2-4. Last time we had to think about trigonometry and sines and cosines of 45 degrees. Well, let's just apply this. Ke. Q times Q. So now this is the one where you have the negative Q times a positive Q, so I'm going to put the negative out here and Q squared out there. And then the separation is separation cubed. Now the separation is what? It's not just A, it's a square root of 2 times A. So we just have to cube that. That's A cubed. The square root of 2 cubed is 2 times the square root of 2. 2 times the square root of 2A cubed. All right. And then we multiply by the vector that goes from here out to there, R 2. What is that vector? It's just A on the x-axis and A on the y-axis. It's just A I hat plus A J hat. And that's actually it. You're now done with F2 to 4. There's nothing else to do. To get the total answer for F4, we have to add the components, so we need the x components in common. So let's see here, the I hat is the x direction, so we have Keq squared over A cubed, although it's actually a squared, those will cancel. So it's 1 times keq squared, or it's 1 times keq squared over a squared. 1. And then what is this going to be? The a's cancel, so it's minus keq squared over a squared, and there's a 2 square root of 2 in the bottom. So let's say minus 1 over 2 square root of 2. Right? And then everything else is the same, keq squared over a squared. That's the I hat component. And then I'll just skip down here to write the j hat component, and it's going to be exactly the same. In terms of keq squared over a squared, the a's cancel, it's going to be a 1. And then this is minus j hat, the a's cancel. So you have left over a 1 over 2 square root of 2. Minus 1 over 2 square root of 2. keq squared over a squared j hat. And that's the answer. That's the same as the previous answer. Written slightly different. You don't see how it's the same. The only thing you need to know is 1 over 2 square root of 2. Well, what is that? 1 over 2 square root of 2. We can always multiply it by 1. So we can multiply it by the square root of 2 with the square root of 2. That's just multiplying it by 1. And what is that? That's a square root of 2 over 4. Right, so that's the term we had when we solved it before. But you can see it's identical. So this is the way to do it. There was no inspection. We never even thought about what this angle was. Right? We put that information in when we put in our 2-4. So you're allowed to do this if you understand that the force still goes as 1 upon r cubed, r squared. It does not go as 1 upon r cubed. It goes as 1 over r squared because there's another magnitude in the unit vector, in the direction vector. All right, good luck.